Hello everyone, welcome back to the latest session. In the last session we discussed aspects which I guess are traditionally not discussed but are actually much more important and relevant to the world we live in and the challenges that we face, right. Again, moving on to the traditional aspects, right. Before we go further, we need to look at or understand, let's say, the life cycle of lakes. So, lakes, like human beings, let's say infants, adolescents, teenagers, middle aged, and then elderly, right. They also have different stages. Let's understand what they are. A newly formed lake, we call it, looks like oligotrophic. Mature lake, first meso and then eutrophic, and then it becomes a meadow or marshland, and then once it's completely filled up, it's dry land, right. So, infancy to elderly age, let's see, right. Oligo, meso, euphotic, right, eutrophic, pardon me, right, oligotrophic, mesotrophic, eutrophic, and so on and other, and dystrophic, I guess. So, that is something we wanted to talk about: oligotrophic, mesotrophic, eutrophic, and hypereutrophic, which you do not want to have. Let us see, right. Chlorophyll concentration, let us say, right. Let us just look at the average: 1.7, 4.7, and then 14.3, and increasing above 50. Secchi depth, which will give us an idea about the turbidity, right. Turbidity means gives us an idea about the suspended matter. So, here I can see until 10 meters, visibility drops to 4 meters, drops to 2, and less than 0.5. And the correlation is with phosphorus concentration: low levels, high, higher, and much higher level concentration, right. Algal growth indicator, phosphorus limiting nutrient, and turbidity, let us say, right. So, that is something that to understand here. So, again, one aspect to understand is that there is something called natural eutrophication, right. It is the process in which lakes obviously receive nutrients from the surrounding areas, and they become fertile, and over a certain period they become shallow, right. The additional nutrients obviously are food for algae, and thus the fish also thrive. And the more eutrophic a lake is, the more living organisms or a more diverse ecosystem it can sustain, right. So, that is something you need to, or we need to understand. And also, as it starts becoming shallow, right, as the depth now is like this, right, even more plants can grow, because the area of the lake that is shallow enough for light to reach. For example, light, it will not reach here. Absorption equal to absorbance equal to molar absorptivity times molar absorptivity times path length times concentration of that particular compound that is absorbing light. So, if the path length is too high, absorbance is also going to be high enough. I mean, water will also have its own molar absorptivity, which is not much, but enough. Water with other suspended matter will have higher molar absorptivity and thus higher absorbance. So, the path length, if it keeps on increasing, plants will not have enough area. So, once it is shallow enough, the more the littoral area, I guess, right. Again, to reiterate, eutrophication is a natural process that a lake goes through over hundreds to thousands of years. That is the key aspect, right. It is referred to as lake aging, but again, natural eutrophication centuries, let us say, right. But due to human activity, what happens is that this particular eutrophication process is accelerated, and the time frames we are looking at is decades, let us say. We are talking about hypereutrophic lakes, and that obviously kills everything out there, let us say. And one example was the excessive algal bloom that we saw earlier, right. So, cultural eutrophication wreaks havoc, resulting in excessive phytoplankton production within a short period of time, which we are saying as, or referring to as, algal bloom, excessive phytoplankton production over a short period of time, which finally, after the death of algal bloom, decreases dissolved oxygen, and also reduces the aquatic life diversity, right. So, let us move on. I guess this is something we discussed, but again, what is it that we need to be concerned about, because only then can you tackle the issue. So, here we are concerned about limiting nutrient among nitrogen and phosphorus. It is Lieberg's law of minimum, whichever is the minimum is the limiting aspect or variable. So, Redfield ratio, carbon, nitrogen, phosphorus in most phytoplankton by molar scale is 106 is to 16 is to 1. 106 is to 16 is to 1, right. stoichiometry of photosynthesis, I guess, okay. Yes, carbon, nitrogen, phosphorus, and I think molar scale it's okay 7:2, not 2 pardon me, 7:1. And Liebig's law of minimum, growth will be limited by the availability of the nutrient that is minimum or least available relative to the requirement. So, we know that it has to be or 16:1. So, if it is greater than 16:1, what does that mean? I mean, let us say if it is 20:1, what does it mean? And let us say if it is only 10:1, what does it mean? So, this means that there is much more nitrogen and not enough phosphorus. Here it is nitrogen by phosphorus ratio, right. So, give more nitrogen, no phosphorus. So, in this case, phosphorus is the limiting nutrient, and in this case, what is the limiting nutrient? Let us say compared to the need, we see that nitrogen is the limiting nutrient because there is not enough nitrogen, right. Hopefully, I did not just make a blunder, but again if I did, you can correct me, I guess, right. If water has a dissolved N by P greater than what is this 16:1, then water is phosphorus limited, and so on and so forth. So, I guess what we just discussed, let us say, right. So, let us move on. Controlling factors, obviously you need the other nutrients too, but nitrogen and phosphorus are typically the limiting nutrients because all these in the relevant concentrations that they are needed are typically present, right. And most marine systems typically along the coast, right, ocean coast are nitrogen limited, and those within or inland are typically phosphorus limited. And what do we see that? It is estimated that total phosphorus concentration in lake water should be around or below 0.015 milligram per liter, which is pretty low to prevent algal blooms. Let me bring up the phosphorus concentration in our sewage water later on, okay. And here we have an example. I believe we already looked at this in detail earlier, but let us just look at it and see what some of the applications are. So, for example, I guess we are talking about what do we say, phosphorus coming into the lake, phosphorus going out of the lake, the concentration coming in, concentration going out is given, the flow rate of the water coming in and going out is given, mass loading as in phosphorus is being dumped into the lake, let us say by some industry in grams per second, and phosphorus is also settling along with sediment at settling rate of this Vs, right, and surface area is given A. So, with these assumptions we are trying to calculate what the phosphorus concentration is, let us say at steady state or at any point. So, mass balance equation, we know this accumulation term is equal to mass coming in and minus the mass going out plus volume into transformations due to formation or loss, let us say, right. So, if it is steady state, you can obviously turn this out to be 0, right. Again, how are we going to model the lake? Here we are going to assume that it is completely mixed, right. So, completely mixed flow reactor or continuously stirred tank reactor, as in we assume that within the control volume your particular concentration is the same or the system is homogeneous within your control volume, and that it is obviously continuously mixed. So, that is what we have, and more importantly, to differentiate from a batch reactor where there is no mass coming in and going out, here we have continuous flow coming in and going out, right. So, we are assuming that the lake is CSTR, and more importantly because it is continuously mixed, the concentration leaving the reactor is the same as the concentration within the reactor, let us say. So, that is a key aspect which will allow you to solve for the relevant equation. So, substituting C with phosphorus, P for phosphorus. So, this is what we have for that particular scenario out there. V dP by dt is equal to Q into phosphorus coming in minus Q into phosphorus going out, and there is mass loading in terms of S, the units are grams per second. Even here let us say the units will be grams per second as in mass per time, concentration is mass per volume, into volume is mass, mass per time, right, mass per time. So, every set of variables here is in mass per time, I guess, right, and here also it is Vs meter per second, let us say, and area is equal to let us say meter square, and phosphorus concentration is mass per volume. So, volume will cancel out. So, mass per time, let us say, right. So, that is what we have out here. Let us move on. So, some of the aspects that we just discussed, loading from point source, concentration and so on and so forth, we can, since we looked at this earlier, I will skim through this. Obviously, at steady state, right, steady state this will be 0 and I can just play around with this variables, and what is it that I am trying to find out? I am trying to find out this P, right. So, I guess C infinity, the concentration of phosphorus in the lake, which was P until earlier, now is we are representing by C infinity. I should have mentioned it as just P. So, it is obviously going to decrease with what do we say, flow rate, but again you have flow rate coming in here also. So, if more of it settles down to the bottom, then the concentration of phosphorus in the lake will decrease, or if less phosphorus is coming in, then also the concentration in the lake will be lesser, I guess. So, if you are talking about temporal variation, so with time, and then you solve it, I guess this is how it will look. So, to reach a steady state concentration, let us see how much time will it take, that is one aspect. Let us say if given certain conditions, let us say how much time will it take to reach from here to here. So, that is one aspect, or once it is at the steady state initially, if you stop a flow or such, how much time will it take to come back to another steady state or such. Let us say again different ways to do it. Let us say for example, usually this is the case, but I want it to be here. So, what is the level of treatment required to bring it down from here to here? Again different what do we say, scenarios to ask questions, let us see. So, here we have a particular question, a phosphorus limited lake with the volume of this and surface area of this is fed by a 10 meter cube per second river. Phosphorus concentration coming in through the river is this, and the settling rate of this particular phosphorus is given. So, estimate the total steady state phosphorus concentration in the lake. This is pretty straightforward, mass balance and apply. We already have the equation, but I will probably not provide such petty equations to you in the exam. Anything from mass balance we expect you to derive. How would you classify the lake? We know that for different phosphorus concentration we can classify it as oligotrophic, meso, eutrophic and so on and so forth. And then what is the percentage or level of P phosphorus removal required to keep the phosphorus below 0.05, as in there was one point source. Where is the point source? Is there a point source? Okay, it is a point source. I guess we are calling the river a point source, which it is not really the case. Okay, I think I am missing some information. Let us see. I mean this is the point source I was referring to. Did I have that point source? So, Vs is given settling rate 10 meters per year. We are changing that into meters per second. So, phosphorus point source was or is given, it is 1 gram per second. So, in this question I should also have mentioned that phosphorus is coming in as a point source of at 1 gram per second, right. So, we plug that in, phosphorus concentration at steady state is equal to flow rate coming in, phosphorus concentration coming in, point source by Q plus settling rate into surface area. So, we have that particular concentration, looks like it is 0.031 gram per meter cube. So, according to this relevant table that we discussed earlier, so that is going to be equal to 31 ppb. So, it is like meso to eutrophic, I guess, right. Again I am not going to ask you to mug up values. So, that is something to please note, right. So, rearranging and solving for S, because I want the P in the lake to be 0.015 gram per meter cube or only I guess 15 ppb. What is the S going to have to be? So, I am solving for S and looks like instead of 1 gram per second, if I want only 15 ppb, it has to be 0.43 gram per second, let us say, right. So, the percentage removal, I guess you can calculate that. So, how do we restore the lake? Cut off all inflows to the reservoir will never work, right, and it will dry up too, but it will never work. Removal of carbonaceous, nitrogenous and CBOD or carbon, nitrogen and phosphorus from wastewater that is coming into the lake. This is something that can be done, but in India that is an issue because we do not have sewage lines and such sewage network. In most villages and towns you have diffuse what do we say, sources, number of non-point sources of the waste coming into the lake and such. That is why this is easier said than done, but now we are well on that particular path with respect to establishing the sewerage network for at least tier 1, 2 and 3 cities and towns, let us say. Right. So, let us move on, and obviously afforestation in the catchment area to decrease the effects of runoff. Soil conservation goes hand in hand with afforestation. Again, that is why obviously you do not want to cut down your trees, and you are need to learn spellings, I guess. Cut down your trees, right, and also you should not pluck out all the grass out there. De-weeding, removal of nitrogen and phosphorus. Aeration, as in if the lake is remarkably low in oxygen, you can provide air to start kickstart the ecosystem, let us say, right. So, I guess with that I am out of time, and before I move on to the next topic, which seems to be emerging contaminants, I guess I will end my session for today, and thank you.